Oh hey, didn't see you there. Too busy testing Boyle's law. Let me take you inside and show you what we're really going to be talking about. Now that we're inside, you may be wondering why I had a paintball gun. That has nothing to do with this project. We're actually going to be talking about the combined gas law, which is, believe it or not, a combination of these three laws. So I'm just going to do a quick recap. Boyle's law is when the volume of amount of gas varies inversely with applied pressure when the temperature is constant. Charles' law is the volume of amount of gas varies directly with the temperature in Kelvin when the pressure is constant. And Gay-Lussac's law is when the pressure of an amount of gas varies directly with the temperature in Kelvin when volume is constant. Now these three laws come together to form the combined gas law. Bamboozled, you thought I was over there, but I'm actually over here. But in all seriousness, the combined gas law states that the volume of an amount of gas varies directly with the ratio of temperature in Kelvin and pressure. For our purposes, we'll be using this equation, which states the initial volume multiplied by the initial pressure divided by the initial temperature is directly equal to the final volume times the final pressure over the final temperature, which we'll go into later. Now, this is a graph that shows how each of these are directly proportional. Bamboozled again. But here we are. We're going to go into the modified example from Ms. Romero, which states a gas has initial volume of 14 liters at 303 Kelvin. The final pressure of gas was measured at 1.5 atmospheres when temperature increased to 310 Kelvin and the volume decreased to 9 liters. The question is, what was the initial pressure? So, moving forward, all the values have been brought into this equation, and from the original equation, we have derived this new equation which allows us to find the initial pressure. The initial pressure is equal to the final pressure times the final volume times the initial temperature divided by the final temperature multiplied by the initial volume. So to solve this, we take the final pressure of 1.5 atm multiplied by 9 liters multiplied by 303 Kelvin. All right, and then we take the final temperature and initial volume and we put that on the bottom, 310 Kelvin multiplied by 14 liters. The liters will cancel and the Kelvin will cancel. And in the end, our initial pressure is equal to 0.94 atm. And now we have a demonstration to show you what this would look like in the real world. Bam, it went through the freaking cardboard. So now we're here with our practical demonstration, right? So we want to try and get this egg into this bottle. But as you can see, the egg just doesn't want to go in because it's too thick. So what's our solution? Fire. Okay, so you're asking yourself, why fire? Just watch and see. Is it on fire? Oh, it is. All right, it's on fire now. And oh, well, it went in a little too fast. So you need me to explain it, right?
Yeah, explain it for me.
Well, I guess we're going back to the whiteboard then, so I can explain it. So now we're back at our whiteboard. We have this beautiful representation of our bottle and egg. But the thing is the pressure inside the bottle and the pressure outside the bottle is the same, which means the only force acting upon our egg is gravity, which is no good because it just won't go in. But once we add this fire here, this beautiful representation of fire, the temperature and pressure inside the bottle is going to increase drastically. And because the volume is limited, the only way for the pressure to equal the outside pressure is for our molecules to fly up and push the egg out of the way until until the pressure has stabilized. But once this fire dies down it's gone, right? The pressure inside the bottle is going to decrease drastically, as well as the temperature, and which means that the outside pressure is much higher than the inside. And the only way for our two pressures to stabilize is if this egg gets pushed all the way into the bottle, and allowing oxygen to flow in, causing equal pressure. If you still don't get it, future Aaron will try to explain it. And yeah. Oh yeah, roll the credits.